hopefully you found some success with algebraic vectors. That obviously it involves a little bit more algebra than it does drawing pictures. And so we'll just do some questions in this one. So in the first one here, we've got a u vector, but then we've got a v vector that's written a little bit differently. Can anyone tell me what the v vector actually looks like if it was in component form? So you see 2i minus 3j and 4k. Oh. Don't be shy, people.
Would that be?
Oh, someone's going to try it. Write it. Sweet. 2 negative 3. Very nice. Perfect. Good job. Thank you. Was that Sam?
Yeah.
Excellent. Good job. There you go. This thing actually does work. All right. So yes, perfect. He said it is 2, negative 3, 4. Be very careful. Sometimes the textbook likes to mess you up and put the order of those in different orders. So even though the k might be first, the k still represents the z value. Okay, so don't get fooled by that. That's a good little hint for tomorrow's test. Okay, make sure you have the order of the I, J's, and K's. Doesn't matter how it's presented to you. The I goes with the X value, the J goes with the Y value, and the K goes with the Z value. So then what we're going to do here is 3u minus 4v. So 3 times u, so the u value is negative 2, 3, 1, minus 4 times the v value, which is 2, negative 3, 4. And how do I get one that's 3 times bigger? What operation do I have to do?
Rainbow.
Yeah, it's exactly like rainbow because each component has to be 3 times bigger. So if we're going to go 3 times that, that becomes a negative 6, a 9, and a 3. And then here, there's 2 ways to do this. You could rainbow a negative 4, or you could just rainbow the 4 and subtract. Both of those are equally correct. So I think I'm just going to rainbow the 4 and then subtract after. So if I rainbow the 4, that'll be an 8, a negative 12, and a 16. And then I'm going to subtract. If I had rainbowed the negative, then I'd be adding. Okay, but let's keep it like that. So negative 6 minus 8 is negative 14. 9 minus 12 is 21. And 3 minus 16 is a negative 13. How did I do in my math?
I got
Good?
that.
Okay, good. And just as a heads up, I am going to give you notes, solutions of all these. So if you'll notice here, I have a notebook file with these solutions already done. So I'll share this with you afterwards, and I'll also share what we do on the Google Meet. So don't stress if I happen to go along and you miss something I've written down, okay? All right, so actually what I'm going to do here is I'm just going to duplicate this to give me some more room. Oh. And then I'll erase this. And we'll go off and tackle the second one. Okay, in the second one, we're taking the absolute value of negative 2u minus v. So negative 2 bracket, the u value is negative 2, 3, 1, minus the v value, which is 2, negative 3, 4. And we have the absolute value of that. So the first part of this is going to feel exactly like A. I'm going to rainbow a negative 2. So becomes a 4 and a negative 6 and a negative 2 minus 2, negative 3, 4. Again, you could rainbow a negative 1 if you wanted, and that would end up adding them instead. Oh, I forgot to slide to the next page. Sorry. There we go. Okay, and then we're going to subtract So 4 minus 2 is 2, negative 6 minus 3. And this is probably where I see the most mistakes on tests or assessments, is little mistakes like that. So it's 6 minus 3. So it's like subtracting a negative or subtracting cold, which makes it hotter. And so that, of course, is negative 3. And negative 2 minus 4 is negative 6. Okay, so the first part is just doing a little bit of rainbow, and we end up with this algebraic vector instead. And then I have these absolute value bars. And what does the absolute value bar tell you to do?
Take the square root of the squares.
That's right. Okay, so we're finding the magnitude of it. We're figuring out how long this vector is. So the square root of the squares will allow us to do that. Okay, and that's just a fancy way of doing Pythagorean theorem. That's where the square root of the squares comes from. But the beauty is if it works in 3 dimensions as well, in 2 dimensions. Is this one in 3 dimensions or 2 dimensions?
3.
3, because there's an x, a y, and a z. And this is the huge advantage of algebraic vectors. It allows us to do 3-dimensional vectors, where drawing those in geometric vectors is way, way harder. All right, so I'm going to do the square root of the squares. So it's 2 squared, which is 4. Maybe I should just show this first step. After this, I probably won't show this step. But 2 squared plus negative 3 squared plus 6 squared. Most of you will probably just square it in your head as you're writing it down. So say 4 plus 9 plus 36 equals the square root of 49, which this time, and total fluke really, we got a number that's nice. Okay, if you get like the square root of 50 or the square root of 48, you'll have to either use a decimal or leave it as a root function. Okay, I'm not going to stress too much about simplifying roots like you did in grade 11. If we were in class, I'd sort of stress that a little bit more. But for your test tomorrow, if you want to leave it as root 49, or well, not root 49, but if you had root 48, if you want to leave it as root 48, that's fine. Okay. All right, any questions for number 5 then? All right. So let's move on. So there's, I just get those backwards. So there's 5A, and I'll delete this one. And we'll move on to number 9. I know these are out of order, but I'm sort of doing them as they would appear on your test. So that's why we're doing there. Okay, so U vector, we've already seen something like this. The U vector actually is 5i, so we would write the component as 5, 3, and 7. And then the V vector, this one looks a little bit different. Could someone tell me what the V vector is?
8, 0, and negative 7.
So why is it 0, Maya?
Because the J isn't in there, so we just assume it's 0.
That's right. Perfect. Okay. And if you saw this on its own, even though there's 2 components, there's just an 8i and a 7j, or 7k, excuse me, that because you have that k value, it tells you it's a 3-dimensional vector. Okay. If it was just 8i and 7j, then it's 2 dimensions. There is no k value. But this one, even though there's only 2 components, it's still in 3D. Okay, or 3 space. All right, dot product. Who can tell me how to do the dot product? Everyone's so shy.
You multiply the individual terms, so 5 times 8, 3 times 0, and 7 times negative 7, and then instead of like putting the commas in between, you like add and subtract them to get one value.
Perfect. Good, thanks, Tara. Remember that dot product produces a scalar quantity, an actual size, whereas cross product produces a brand new vector. Okay, so we're going to multiply the x's, the y's, and the z's, and add them as opposed to the cross product where we would get a new vector. All right, so here it's just 8 times 5, which is 40, plus 3 times 0, which is 0, and 7 times negative 7 is a negative 49. So you would be adding the negative 49, and then, of course, adding those together, you get negative 9. no problem if we get negative dot products, we can get positive or negative dot products. If you recall back to geometric vectors, if we ended up with a negative dot product, that means our answer was going in the opposite direction. So apparently these vectors, if we could draw them or see them, we would see them in as this vector going in the opposite direction. Okay. All right, good. So just plain old dot product there. And let's move on to number 13, where we're going to do some cross product. So I got a few comments, emails, and texts about my lesson about the cross product. Some people didn't get that I was being a little sarcastic with the formula, and some people did. But it's definitely a formula that I wouldn't have you have to memorize. We definitely need that sort of shortcut or little gimmick that we would do off the side to try and figure out the cross product. Okay, so would anyone like to try and tackle this, the cross product, or at least tell me the steps that I need to do to try and do the cross product?
You can do the shortcut, so you can write out your u values, so 2, 7, -1. Oops. And then repeat that again.
Okay, so 2, 7, -1. Repeat it, 2, 7, -1.
And then below it, you write your v components, so -4, 5, and 1. And then you repeat that again.
Excellent, good.
And then you cross out your front and you like your first one and your last one.
Okay.
I don't know if someone else wants to. I can keep going, but someone else can do it too.
I think they're giving you this birthday wish.
Okay. So then you do 7, like you crisscross them, so down and then up. Yeah, so 7 times 1
Yep.
7.
Yep.
And then 5, -5. So 7 minus 5.
Good. So do you remember what I called that in the video? That little X, that cross? Anyone?
Down product,
Down.
down product, up product.
Yeah, down products.
Go up minus up product.
Minus the up products, that's right. Okay. All right, so you're absolutely right, Maya. You did the 7 times 1 get me a 7, and the 5 times -1 is a -5, but of course you're subtracting that part. So I don't know about you guys, but I kind of sort of do that subtraction while I'm thinking about it right now. I don't know if you do or not. So I would do 7 minus -5, which is what?
It's 12.
Right. Okay, and then I sort of go off and do the next one. Totally up to you. You might want to do all the other ones in between. Maya, you're doing great. Why don't you keep going?
Sure. So negative or +4, sorry.
Yes.
-2.
Good, which is going to get us a 2 there. Excellent. Keep going.
And then 10 minus 28. Minus 28.
Yes, excellent. And even by saying the minus, it reminds you that it's a plus, which is going to be 38. And as I mentioned before, the dot product, the cross product is going to get you a new vector. And so make sure we write it as a new vector. Okay, so and there's your answer. That is the cross product. When we did cross product in the last unit, we had to go off and use our right-hand rule to try and decide if this is going out or into the page, but this component will take care of that. If you could draw this three-dimensionally, you would see how it was relative to you. So you don't need to worry about direction. This is all taken care of in your answer. Okay, and next unit, we're going to be doing a little bit more visual stuff, and you'll be looking at the stuff in 3 dimensions. So I've got some software lined up for us to be able to see these in 3 dimensions. But right now, we're just worried about the skills of using algebraic multiplication and stuff. Okay, good. Any questions about cross product? All right. So those questions sort of take you through what number 1 is on the test. Number 1 is going to be just a couple of vectors there, and you'll need to do some adding, subtracting, finding the magnitude, a dot product, and a cross product. Okay. So, and then we're going to move down. This number 10 is much like what we'll see on our test for number 2. On our test, we'll be asking to find the angle between two vectors. And so there's a formula for this. Anyone other than Maya, because she's been put on the spot a couple of times. Anyone else want to take the formula for this?
The absolute value of u times the absolute value of v cos theta is equal to the dot product of u and v.
Okay, so, oops. So absolute value of u, absolute value of v equals, oops. Sorry, what did you say, Tara? I'm getting it backwards here.
The absolute value of u times the absolute value of v cos theta is equal
Right.
to the dot product of u and v.
Thank you. Good. And the reason she's told us that is that actually comes from last unit. But if we're figuring out the theta, just the theta, the cos theta, what operation would you do now?
The dot product of u and v divided by the absolute value of u times the absolute value of v.
Excellent. Good. And some of you may have just gone straight to this formula, but it does come from our definition of dot product from last unit. Okay, so that is our formula for this. Now we're just going to substitute in the values and actually do the operations. So let's try and do the dot product without me actually typing it in. So on the top, we're going to be multiplying, we're going to be doing the dot product of these two, this and this, which means we're going to multiply the x's together, the y's together, and the z's together and add it. So multiplying -5 times, or sorry, -1 times -5 is 5, plus 2 times 10 is 20, and finally plus -3 times -15 is 45. And that's all the dot product on the top. And then on the bottom, we're going to do the magnitude. So much like we did in the first question, the square root of the squares. So it would be the square root of -1 squared, which is 1, plus the square root of 2 squared, which is 4, and the square root of -3 squared, which is 9. And similarly, the square root in this guy of -5 squared is 25. And 10 squared is 100, and 15 squared is 225. On the top then, any questions for there? Okay, just doing all the same questions that we did in the first few examples, but combining it all in this formula. Okay, so on the top I've got 70. And in the bottom, I've got 1 plus 9 is 10, plus 4 is 14, and 25 and 225 is 250, plus 100 is 350. And this is really then an exercise on your calculator, being able to punch this in your calculator. Be very careful that you are doing the operations on the bottom first, so that when you divide, you can divide the whole thing. The other thing you could do, if you punch this in your calculator, I'll see if I can pull up my calculator here so you can watch it on the screen. Okay, so because I did get a couple of texts and emails about this, so let's just move this over here. Okay, so in a couple of ways you can do this. If you're going to go 70 divided by, then you got to make sure that you have both of these in brackets on the bottom. So this is one idea, the square root of 14, and then times the square root of 350. But you see that the whole bottom is in brackets because you're dividing by the whole thing. So you could have that, which ends up being 1. This is kind of a unique question. The other way you could do it is this. This is kind of when I'm getting lazy, I do this. I go divided by root 14, and then I push the divide by sign again, because you're actually dividing by this and dividing by 350. So this is kind of a little shortcut instead of having to do those brackets, you're doing division twice, and you'll still get the same answer. Okay, so it's kind of unique that this one came down to 1 cos theta equals 1. Usually when we've done these, we got some weird decimal. And then, of course, we need to do the inverse cos of that weird decimal. In this case, that weird decimal is just 1. And we get an answer of 0. So it turns out the angle between these two examples in number C is 0 degrees. So is there any clues in this question that would have hinted at the fact that the answer was 0 even before you began?
It's all times 5. It's just the same thing.
That's right. So if you take u values and multiply it by 5, you get this, which means this v vector is just 5 times u. So v is actually, that's right. Yeah, I wasn't sure if we had that language yet. It's a scalar multiple of it. Okay. So if it's a scalar multiple of it, it means it must be going in the same direction. So if we graphed u, a 3-dimensional vector like that, v would be simply 5 times that size in the same direction. So now it becomes a little bit obvious of why the answer was 0 in this particular case. Okay. Not too often do we find the angle and we get a nice little number like this, but all the steps we would have done would have been the same anyways. Okay, I just thought this would be a good question to sort of answer a couple of things in there. All right, so any questions?
If we notice that before we start the question, is it okay to just say we know the angle is 0 because it's a scalar multiple?
Yes, yeah. And you'll just be laughing at me because I gave you an easy question. So good for you. Yep. Okay. Any other questions though about finding the angle between two vectors? Chances are in the one that I've set up for you, you'll get an actual angle. I just thought this would be a neat one to do this morning. Okay. Moving on to number 11. So in number 11, it says that these two vectors are orthogonal. Does anyone tell me what orthogonal means?
Perpendicular.
Good. Okay. And this, I'm using this example to review a bunch of things. So you might see something like this pop up on its own question or someplace else on the test, maybe in a thinking question type thing, which I'm sure you're all excited to hear there's going to be a thinking question. But yes, orthogonal means that it is perpendicular. And what is the quickest and easiest way to figure out anything when you're talking about perpendicular? Or any relationships about perpendicular vectors? So either the silence is because everyone's being polite or nobody really knows what I'm talking about. So there is some algebraic operation we can do to prove that two vectors are perpendicular. And we'll need it for this question.
Oh, set it to 0 and then solve.
Set what to 0?
The
dot product.
Yeah, like the dot product. So it'd be like -3, 6a.
Yes.
Times b, -2, 4, and then whatever it equals, you have to see if it solves for 0. Like
because we know that the angle between them is 90 degrees, the cos of 90 is 0. So it makes the right side of our dot equation 0. So we can set it.
Excellent. Good. Okay, so that was all the explanation behind this. We saw it a couple of times throughout the unit. Had we been in class, I would have been stressing this almost daily. Okay, and this is when two vectors are 90 degrees, their dot product is 0. And Tara had a good little explanation there. If they're 90 degrees, then you're taking the cos of 90, which is 0. Okay, so this is going to pop up maybe in this question or maybe someplace else where I might ask you to convince me that something is a right triangle or a right angle or a right rectangle or a right two perpendicular lines, all of those would require a 90-degree angle, and you would take the dot product and set it equal to 0. Okay? Or just take the dot product and find out if they're 0. If you find out they're 0, then you know that they are perpendicular. Okay, did everyone get that part? Because that's a big, important part for your thinking question on the test. Okay, so if they are perpendicular, like they or orthogonal, then their dot product is equal to 0. All right, so in this case, exactly how you suggested, Maya, we're going to actually do the dot product. So it would be the x's times the x's. So -3 times b is -3b. The y's times the y, which is 6 times -2 is -12. So you're adding -12. And then a times 4 is 4a equals 0. If you were trying to solve for one of these, you could solve for a, for example, and say that 4a equals plus 3b plus 12. Okay, moving those to the other side, taking the inverse operations. And it turns out then that there's actually lots of answers for this. There's multiple answers. You can choose any value for b in this question. So if I chose, let's say b equals 1. So I sub that in. This would be 3 equals 1 plus 12. And that would be, oh, 1's not a great number. Well, let's keep going though. 3 plus 12 equals 4a. Divide everything by 12, so 4a equals 15. Divide everything by 4, a equals 15 over 4. And there is a value for a and b that would produce 2 perpendicular vectors. We maybe, if we had chose b to be 0, it would be even easier. 4a equals 3 times 0 plus 12. So 4a would equal just 12, and a would equal 3. And there's another set of a and b values that if we plugged it in would get 2 vectors that are perpendicular. You can imagine that there is thousands and thousands of answers to this question because of how many perpendicular vectors they are. All right, if let me see. Hopefully you can see me kind of on the screen. So if I've got a vector like this and I wanted to draw a perpendicular vector, there is one there, but all sorts of different vectors could lie on this vector and still be perpendicular. Okay, so there's multiple answers. And this vector here could be a small one, a short one, and also anything that is on the other side of this vector would also be perpendicular. And finally, I could take this pen here and this other pen here and spin it around, and all of these would also be perpendicular. So there's just an infinite amount of perpendicular vectors in 3 dimensions. And that's something we're going to really pay closer attention to next unit. All you're really learning in this question is how valuable it is to know that their dot product is equal to 0. Okay? Questions there? All right. So I could have asked this question as the review today. I could have just given you 2 vectors and say, are they perpendicular? And if you don't know, you would just take their dot product. If their dot product ended up being 0, you could say they're perpendicular. If it's not 0, then they're not. Okay? All right. Good. Any questions for that? All right. Good. All right. So our last one here is from number 15. And you'll see that I've actually edited the question out of the textbook from 15. All right, 15 is gives you 3 points of a quadrilateral, or sorry, a parallelogram, which is also a quadrilateral. I've changed this. We're not going to find the 4th vector, or 4th coordinate, excuse me. We're only going to find this as a triangle. Okay. This question here we normally would have done together, but it's a really long question that I thought was a bit too much to put in a video. And so we're only going to look at this as a triangle. and answer 2 questions about it. So the first thing I'm going to do is not, I'm just going to say these 3 points are a triangle. We're going to find the perimeter of it, and we're going to find the area of this triangle. So I should actually scratch this out and say triangle instead. Okay. All right. So I'm going to plot these points. This is merely a sketch. We have no clue what this picture actually looks like unless you wanted to visualize it in 3 space, which you're welcome to do, but we're not going to do that. So I'm just going to go and plot 3 points that kind of look like a triangle. And I'm just going to call them P, Q, and S. There's nothing special about the way I've set this picture up. I could have put the P here and or here or here or whatever. Normally you would use 3 letters, sequential letters, so P, Q, and R, but this question has the R missing. So we're just going to go off with it and say P, Q, and S. All right, so we're going to find the perimeter of this, which means we need to find the length of all of these sides. So what you're going to do is pretend that these sides are vectors themselves. Okay, so each of these are vectors. You'll find those vectors and find the length of them. It doesn't matter if you decide to call this vector u, or if you did it in the opposite direction and called this vector u. Because you're finding the magnitude in this first part, that direction doesn't matter. It will matter later on for the second part. Okay, so let's just call them, I'm just going to get rid of some of this stuff. Let's just call this vector u. So over here, I'm going to say vector u is actually the same as calling it PQ. Okay? How do I find the actual vector PQ? Because you'll notice that I'm not given any vectors in this question. I'm only giving coordinates. So how do I find the vector PQ?
Q minus P.
Excellent. And so we're just going to take these coordinates, Q minus P, and subtract them. So 3 minus 1 is 2. Negative 3 minus 1 is negative 4. And 4 minus 1 is 3. Okay, be very careful in this step. I might encourage you to even do it twice, just to make sure you haven't made a mistake in that thing. We're going to be using this vector a lot. And so if you've made a little mistake here, that mistake is going to follow through for the whole rest of the question. Let's now go off and I guess I'll just call this one here, call it vector V. And that looks like PS. So PS would be S minus P. And so now I'm going to take the S coordinates and minus the P coordinates. So I'm subtracting 1, 1, 1. So this is going to be negative 2 minus 1, which is negative 3. 4 minus 1 is 3. And 5 minus 1 is 4. And again, I'm just going to double check that I've done that right. And finally, let's go and call, oh, I don't know, this one maybe. Let's call this W. So W equals QS. And so that's going to be S minus Q. And so again, we're going to do S minus Q. So we're going to subtract the X values. So negative 2 minus 3 is negative 5. 4 minus 3 is 7. And 5 minus 4 is 1. And I've got each of those vectors. Okay, good. Any questions so far?
I have a question. How do you know, doesn't matter. I think you talked about this though. Like, can you do SP or
Absolutely.
SP, and then just do the opposite, but you're going to get a different number for your components.
Right. So let's just talk about this last one. Had I gone off, I just drew randomly QS, but had I drawn the vector the opposite direction, it would have been Q minus S, right? Because that would have been SQ. And then what this would have been ended up being was 5, -7, -1. Okay? Because you'd be doing the Q minus the S instead. Now, you're absolutely right. This does produce a different vector, and my picture suggests that, right? If the green vector is going one way, the black vector is going the other way, then we should get a different vector. But because we're finding the perimeter, we're going to find out how long it is. So the length of the green vector is going to be the same as the length of the black vector. Do you agree with that?
Yeah, so it's not going to matter which way you're going because you're just...
Right, right. So far. Okay, for part B, or for the second question, it is going to matter. But right now, because I'm finding magnitude, it doesn't matter which one I choose.
So like for the first part, we could literally go PQ, QS, SP.
Absolutely. Yes. Okay. Now, when we get to the second part, you're going to see why I kind of chose two vectors coming from the same point.
Oh, because then you don't have to do the work twice later on for part B.
Exactly.
Okay.
Yes. Okay, so the sneak peek is when I go off and find area, I need to do the cross product. And the cross product has to have the two vectors going from the same point.
Okay. So like whenever we do it, it's good to make sure that 2 points meet.
You might as well, because you're going to need to do it in the second part. So you might as well save yourself some work and do it now.
Okay.
Okay, really good question. All right, so I'm just going to erase that black vector there. Not that it's wrong, just that I'm going to stick with my green one. And now I've got 3 vectors, and I need to find out how long each of them are. So we're going to do the square root of the squares for each. So the red one is going to be the square root of 4 plus 16 plus 9. So that's 29, the square root of 29. I'll leave it as the square root of 29. You could get a decimal here, but let's just leave it like that for now. And then my blue vector is the square root of 3 squared, or negative 3 squared, which is 9, plus 3 squared, which is 9, plus 4 squared, which is 16. And that is going to be 18, 24, 34, sorry. Right, 34? Okay. And then my final one is the green vector, and it's the square root of 25 plus 49 plus 1. There we go, sorry. Okay, and that's 50, 75. And so if we're finding the perimeter is just going to add all these up. So root 29 plus root 34 plus root 75. Now, technically, that's the nicest answer. That's the most exact, precise answer. But if someone asked you to find the perimeter and you gave them this response back, it probably wouldn't mean anything to them. So I would actually go off and do the decimals for each one. Square root of 29, square root of 34, square root of 75, and I would get 19.9 units as an answer. Okay? Questions about that? All right, good. So I'm just going to copy this and create a blank page. Okay, so we're now going to find the area of this triangle. Okay, and so as I hinted at with Maya before, to find the area, we are actually going to pretend this is a parallelogram and find the area of a parallelogram, because the area of a parallelogram from last unit is the cross product of the two vectors that define it. So I'm just going to redraw my picture very quickly. You'll probably do it right on the same picture that you have, but there's that one, and this one. So P, Q, and S. Oh, sorry, I'm on the wrong page here. Okay. You can imagine that there is another point someplace out here. This question actually calls it R. Okay, and that would define a parallelogram. Now, in our last unit, to find the area of this parallelogram, we can find this vector, U, and this vector, V, and if we did their cross product, that would get the area of the whole thing. Okay? But in our question, we're not actually finding the area of the parallelogram. We're only finding the area of the triangle. But I think we can all agree that this triangle is going to be exactly half the size of that. So the area of the triangle is going to be 1/2 U cross V. Can everyone see that? Okay. Now, I've drawn this picture out to just explain it, but really what we're going to do is just do the math on it. Okay, so I need to go back and just look at my picture again. So this is the conversation that I was having with Maya, that in order to do the cross product must have the vectors starting from the same spot. So in this particular one, I've decided to start from P and go out from there. You could have done it from Q or from S, but you need two vectors starting from the same spot, because to do the cross product, the beginnings must be at the beginning. Okay, something like this is not correct. Something like this is not correct. You have to have the two beginnings of the vectors to do cross product. So if I go right back to the way I drew the first one, you'll see that U is coming from P and V is coming from P. So I'm going to use these two vectors, U and V, that both came from P to do my cross product. And all I need to do then is copy it over to my other screen just so I can see it. So I've got the U vector, which I've already done the math on, is 2, -4, 3. And I've got the green vector, W, which is -5, 7, and 1. Okay, so there they are. And so now I just need to, oh, sorry, not W vector. Sorry, the V vector, my mistake, sorry. So I need the blue vector. So the blue vector was -3, 3, 4. All right. Okay, so we're all with me there? So I'm going to actually now do the cross product, do it really quickly, because I know we're coming along. Oops. So 2, -4, 3, and then write it down again, 2, -4, 3. The V is -3, 3, 4, and -3, 3, 4. Okay, cross out the first one, cross out the second one, cross, cross. And just to save some time, I'm going to tell you that the answer to that is -25, -17, and -6. Okay? All right, so that is the cross product. But if I actually go back and I need its magnitude, okay, so the area is actually the magnitude of it. So I need to find the magnitude of that vector. So I'm going to go off and do the magnitude of this, which is going to be the square root of the squares. So it's going to be 25 or -25 squared, which is 625. And 17 or -17 squared is 288. And -6 squared is 36. Add them up and I get, oh, actually, I don't have that number here.
950.
950, thank you. Okay, so that's the magnitude of U cross V. But of course, for me, I need half of that number because I'm finding the area of the triangle. Sorry?
Is it 288 right there?
Yes.
288. I got 949 actually.
I got 949 the second time I did it. Sorry about that.
Oh, no problem. That's okay. I went right to the answer, so I didn't actually, it's somewhere in my calculator that. So, sorry, you said it was 949. 949. Thank you. Okay. So, the area of the triangle is going to be half of this U cross V. So we just did all that. So that's going to be a half of the square root of 949. So you'll punch that square root of 949 in your calculator, take half of it, and I got an answer of 15.4 units squared. Did you guys get that too? Yes, thumbs up. Good.